Okay, in this lecture we're going to finish up our section 11.8 material on derivatives of exponential and logarithmic functions. And in our last couple of examples for this section, we'll look at some applications of the derivatives of exponential or logarithmic functions. So let's consider the following. Suppose that the number of cell phone subscriptions per 100 people in middle-income countries can be approximated by the function f of t, which is 100 over 1 plus 25e to the negative 0.4t, where t equals 0 corresponds to the year 2000. So in part A, we're asked to find the derivative of this function, which represents those number of cell phone subscriptions. So looking at the current form of this function, we see it's a quotient of two functions, so we could make use of the quotient rule, and we're also going to need to use the chain rule to find that derivative. However, if we rewrite this function in the following way, let's say as 100, and then the division by 1 plus 25e to the negative 0.4t, we could rewrite as multiplication by 1 plus 25e to the negative 0.4t raised to the negative first power. So in this way, we can avoid using the quotient rule, and we can just make use of the chain rule. So to differentiate our function by using the chain rule, we have f prime of t is equal to, well, we start by differentiating our outer function. So using the generalized power rule, I can take this exponent and bring it out in front of my function. So when I multiply my 100 by the negative 1, I have negative 100. And then I have the same base, 1 plus 25e to the negative 0.4t, now raised to the negative 2 power. We decrease the power by 1. But now I have to make use of the chain rule and multiply by the derivative of this inner function. So on the end, we're multiplying by, the derivative of 1 is 0, and the derivative of 25e to the negative 0.4t would be 25e to the negative 0.4t. And then using the chain rule again, since this exponential is a composite function, we have to multiply by the derivative of that innermost function. So the derivative of negative 0.4t is negative 0.4. So now let's simplify our work a little bit. We have negative 100 times 1 plus 25e to the negative 0.4t raised to the negative 2. And this last expression on the end, when I have 25 times negative 0.4, I'm left with a negative 10. And then I still have my e to the negative 0.4t. So rewriting this once more to simplify, when I have the negative 100 times negative 10 e to the negative 0.4t, that gives me a positive 1000 e to the negative 0.4t. And then this expression in the middle, where I have this function being raised to the negative second power, well, that is the same as dividing by that function, 1 plus 25 e to the negative 0.4t to the positive second power. So this would be a simplified expression for the derivative of that function f of t. Now, once we have this, in part B, we're asked to find the value f prime at t equals 17 and then round the answer to 1 decimal place. So using the expression for the derivative that we just found in part A, and evaluating at t equals 17, we have 1,000 e to the negative 0.4 times 17 divided by 1 plus 25 times e to the negative 0.4 times 17 quantity squared. Or, rewriting this a little bit, we've got 1,000 e raised to the negative, multiplying 0.4 by 17 gives us 6.8 all over 1 plus 25 times e to the negative 6.8 quantity squared. Now, using a calculator to evaluate this expression, we find that this value is approximately 1.1 if we round to 1 decimal place. Now in part C, we're asked to interpret the answer that we just found from part B. So let's think about what we were finding here. So we evaluated the derivative at the value t equals 17, and we were told in the problem statement that t equals 0 corresponds to the year 2000. So we could start by saying here t equals 17 corresponds to the year 2017, since t equals 0 was the year 2000. So our answer for part B, the derivative of our function at time 17, represents a rate of change of the function f. That is, the rate at which the number of cell phone subscriptions per 100 people is changing. So we can say in 2017, the number of cell phone subscriptions is increasing. Here it would be increasing since our derivative in part B was positive rather than negative. So a positive rate of change means an increase at a rate of approximately 1.1 subscriptions per 100 people per year, since our derivative was involving the variable t. So we're looking at the rate of change of the number of cell phone subscriptions per 100 people with respect to time, so it would be per year here. All right. So in our last example for this section, we'll look at an application involving the derivative of a logarithmic function. So here we're told a person owes $4,000 on a credit card that charges an annual interest rate of 15.9% compounded monthly. So if the cardholder makes no additional charges and makes a payment of P dollars each month, the number of months that it will take to pay off the debt is given by the function f of p, which is 76 times the natural log of p divided by p minus 53, where p is greater than 53. So the minimum payment would be $53. They have to pay at least that much. So here A says find and interpret the value f of 78. So let's look at it here. Evaluating our function f, when p is equal to 78, we would have 76 times the natural log of p, which is 78, divided by p minus 53, So 78 minus 53 leaves us with 25. And evaluating this using a calculator, we have this value as approximately 86 if we round to the nearest whole number, where this value was being measured in months, that is months to pay off the debt. Now, if we're talking about, say, more than a time period of 12 months, it might make more sense to say years instead of months. So this would be approximately 7.2 years. So our interpretation here is if the monthly payment is P equals $78, then it takes 7.2 years or 86 months to pay off the debt. All right. So in part B, we asked the question, would we expect the derivative, f prime of p, to be positive or negative, and why? So let's recall that the derivative of a function represents the instantaneous rate of change of that function. So we're asking if the rate of change of f of p, which represents the number of months it will take to pay off the debt, would be positive or negative, that is, would that time increase or decrease if we were to increase the value of p, that is, if we increase the monthly payment. So here, we would probably expect the value of that derivative to be negative, since an increase in the monthly payment P would result in a decrease in the time to pay off the debt. So increasing the amount that you're paying towards your debt would decrease the amount of time that it takes to pay off that debt. So in part C, we're asked to verify our intuition in part B. So that is find and interpret the derivative of f at p equals 78. All right. So to find the derivative of this function, when we look back at the original function f of p, it's 76 times the log of a quotient. So we could make use of the chain rule together with the quotient rule to differentiate this, or using properties of logarithms, like we saw in the last lecture, we could rewrite the log of a quotient as the difference of two logarithms. So by rewriting our function as 76 times the log of p over p minus 53 becomes log p minus log of p minus 53. And now it's much easier to differentiate this function because we no longer have to make use of the quotient rule. So let's start by finding the derivative f prime of p. So here we have a constant 76 out in front, and we're multiplying by, well, the derivative of natural log of p is 1 over p, minus the derivative of natural log of p minus 53 would be the derivative of that inner function, p minus 53, which is 1, divided by p minus 53 itself. So we see here that this value is indeed negative, since the ratio 1 over p minus 53 would be greater than 1 over p. So our intuition from part B was correct. And once we have the expression for this derivative, we can evaluate at the value p equals $78. So we have 76 times 1 over p, which was 78, minus 1 over p minus 53, which would leave us 1 over 25. And this works out to be approximately negative 2, if we round to the nearest whole number. So the interpretation for this value would be if the monthly payment is P equals $78. The time to pay off the debt is decreasing. Here we would say decreasing since the value of our derivative was negative 2. A negative rate of change corresponds to a decrease in this quantity at a rate of 2, where here the value is being measured in months, per, well, our variable f, or the function f depended on the variable p, which was in dollars, so we would say per dollar increase towards our monthly payment.